Okay, let's dive right into this. Welcome back, everyone, to another explainer. Today, we're unpacking the absolute backbone of building automation systems and HVAC control, the PID controller. Look, if you're a technician, a controls engineer, or even a student just stepping into the automation world, you already know that keeping a massive building comfortable isn't as simple as just flipping a switch. I mean, unless you want half your occupants shivering in parkas and the other half in swimsuits. So we're going to break down exactly what a PID controller is, how it actually works, and most importantly, how you can tame it out in the field. We'll start with some everyday analogies and work our way right up to advanced troubleshooting.
Here is our agenda for today. We'll cover beyond simple on-off control, the core concepts of PID, unpacking P, I, and D, why PI rules HVAC, real-world BAS applications, and finally, tuning and common mistakes. Let's get to it.
Section 1. Beyond simple on and off control, or why basic thermostats fail.
So you might be wondering, why exactly is basic on-off control completely failing your HVAC system? Well, in a small residential setup, a basic thermostat that clicks on when it's cold and clicks off when it's warm, sure, that works absolutely fine. But when you scale that up to a massive commercial building with hundreds of zones, intricate air handling units, and giant chillers, that binary approach is literally a recipe for disaster. It leads to massive energy waste, rapid wear and tear on your expensive equipment, and honestly, just terrible occupant comfort.
Think about on-off control, kind of like driving a car by either stomping the gas pedal all the way to the floor or slamming hard on the brakes. There's zero in between. It's incredibly jerky, right? PID control, on the other hand, is basically your car's cruise control. It makes these incredibly smooth, continuous micro-adjustments to the gas pedal so you maintain a perfectly constant speed, regardless of whether you're climbing up a steep hill or cruising down a valley. It's fluid, dynamic, and super precise.
Section 2. Core Concepts of PID. Let's learn the language of control loops.
All right, first up is the set point, or SP. So, the crucial point here is that the set point is your ultimate goal. It's the exact, specific target value your system is desperately trying to maintain. Going back to our car analogy for a second, the set point is that 65 miles per hour you just locked into your cruise control. Now, in a building context, that might be exactly 72 degrees Fahrenheit for a big conference room, or maybe a very specific static pressure for a duct.
Now, let's see how this builds into an actual continuous loop. A PID controller essentially works by cycling through 4 continuous steps, over and over again, in real time. First, it reads the process variable, or PV. That's what's actually happening right now, like the current temperature of the room. Second, it compares that PV to your set point. Third, it calculates the difference between those two numbers. And fourth, it adjusts the controller output, which tells the system exactly how far to open a valve or speed up a fan to fix that difference.
Step 3 in that loop brings us to a really vital term, error. Now, in everyday life, an error implies a mistake, right? But in control logic, error is simply the mathematical difference between your set point and your process variable. It's just the gap. If you want the room at 72 degrees and it's currently 74, your error is exactly 2 degrees. The entire existence, the whole purpose of the PID algorithm is to calculate that error and relentlessly crush it down to 0.
Section 3. Unpacking PI and D. Time to demystify the algorithm itself.
We begin with P for proportional. The proportional band reacts entirely to the present error. It looks at exactly what's happening right this very second and applies a proportional amount of output to correct it. If your car is going, say, 10 miles an hour under the speed limit, P steps on the gas pedal pretty hard. But if you're only 1 mile an hour under, P just gives it a tiny little nudge. It is all about the here and now.
Next up is I for integral. While P is obsessed with the present, I is looking at the past. It reacts to accumulated error over time to eliminate what we call sustained offset. Imagine you're driving up a really long, steep hill. The proportional response might give you enough gas to almost reach 65 miles per hour, but gravity is stubborn and it keeps you stuck at 63. So you have this sustained offset. The integral component notices this. It goes, hey, we've been 2 miles per hour too slow for a full minute now, and it slowly adds more and more output until it finally nudges you perfectly up to 65.
Finally, we have D for derivative. The derivative actually anticipates the future predicted error by monitoring the rate of change. Think about it. If you're approaching a stop sign, you don't keep your foot slammed on the gas until the exact millisecond you hit the white line, right? No, you anticipate the stop and you ease off early. Derivative sees how fast the temperature or pressure is changing and applies a dampening effect to prevent the system from just flying right past the set point.
So, how does this whole trio actually work together? Well, P acts on the present to give you an immediate proportional response. I acts on the past to correct any of that stubborn sustained offset. And D looks to the future to dampen rapid changes and prevent overshoot. When you put them all together, they create an absolutely beautifully balanced control strategy.
Section 4, Why PI rules HVAC, finding the sweet spot.
Now on paper, full PID control sounds absolutely flawless. But here's the thing, in the HVAC world, we rarely actually use the D. We almost always just use PI control. Full PID can honestly be incredibly twitchy and overly sensitive. PI control just completely drops that derivative calculation, relying entirely on the proportional and integral actions. In our industry, PI is absolutely the gold standard. But you might be wondering, why drop the D?
The simple truth is, the derivative is just way too sensitive for slow-moving HVAC thermal systems. Remember, D is always looking at the rate of change. But heating or cooling a massive room, that takes time. It's inherently a slow process. If someone opens a door and a sudden gust of cold air hits a sensor, the derivative panics at that sudden rate of change and starts violently slamming valves open and closed. So dropping the D keeps the whole system calm and prevents a ton of erratic behavior in our mechanical equipment.
Section 5, Real-World BAS Applications. This is where the magic happens.
You are going to find PI control loops absolutely everywhere in a building automation system. I mean, they're in VAV boxes modulating dampers to manage room temps. They're in massive air handling units, smoothly controlling static and duct pressure so you don't literally blow out your ductwork. You'll see them modulating chilled and hot water valves to maintain precise supply air temperatures, and they are constantly, and I mean constantly, commanding variable frequency drives, or VFDs, to ramp fans and pumps up and down efficiently. It truly is the universal language of HVAC mechanical control.
Section 6, Tuning and Common Mistakes. Let's talk about getting it right in the field.
If a loop is tuned poorly, you get this wild oscillation, which we commonly call hunting. Imagine a chilled water valve for a second. At 0 seconds, the controller panics and just rips the valve 100% open. 10 seconds later, the air is absolutely freezing, so the controller panics again and slams the valve down to 0%. 10 seconds after that, it's hot again, and the valve shoots right back to 100%. The system is desperately hunting for the set point, but keeps completely missing it, just wildly oscillating back and forth. Guys, this destroys actuators and completely ruins occupant comfort.
So why exactly does this hunting happen? Well, here are the most common mistakes we see technicians make. First up, overtuning for an unrealistically fast response. Look, you cannot force a massive boiler to heat up instantly, no matter how aggressive your software loop is. Second, ignoring those inherently slow thermal response times we just talked about. And third, and honestly, this is a massive one, failing to check for mechanical failures first. Technicians will literally spend hours tweaking a PI loop in the software, only to realize the physical valve actuator is actually broken and physically stuck in the open position. You cannot program your way out of a broken valve.
I want you to remember this golden rule of controls engineering. The goal of tuning isn't immediate perfection, it's finding the perfect balance between a slow response and an unstable oscillation. Stable control takes a little patience, you know. You want the system to reach the set point efficiently without flying past it into a state of wild hunting.
So as we wrap up this explainer, I want to leave you with this question. Next time you're in the mechanical room or staring down your BAS graphics and you see a hunting chilled water valve swinging wildly from 0 to 100, are you going to know which part of the PI loop to tame? Just remember your P for the present error and your I for that past sustained offset. Respect the math, respect the physical limits of your equipment, and go out there and tune those loops. Thanks so much for joining this explainer.